Good morning, everyone. We have Faisal Haque here. He's the founder and CEO of Imparé. Faisal, welcome. If you could please introduce the topic.
Thank you, Rahil. Today we'll be talking about testing Terabit Ethernet.
That's great. People would love to know about your background and experience, if you can talk about that.
Sure. I started off at Intel in 1984 working on Ethernet components as well as processors and cache subsystems. Then Growth Networks was started in 1999 and sold to Cisco in 2000. We started working on their terabit routing program. In 2001, we launched the Art of Verification Vera, which is considered one of the two classics on verification. In 2003, I helped participated and led the development of SystemVerilog as chair of the SystemVerilog Assertions Subcommittee. Then in 2006, we published the Art of Verification with SystemVerilog Assertions. 2012, I was leading Qualcomm's verification, and we led the development of Qualcomm's first handset LTE modem. And then 2022, we founded Imparé.
That's very impressive.
Thank you. Okay, so I think getting into the topic right away, why terabit Ethernet is hard to test. So one of the key points of terabit Ethernet is its multi-lane architecture. For example, a 1.6 terabit splits across 4 by 400G slices, and you have four lanes, four FEC lanes, and four SerDes lanes on every slice. So all these lanes need to align. You have also signal integrity issues at 100 gig and 200 gig speeds, which leaves a lot of very thin margins for noise. And then you have to deal with flow control, which is dynamic feedback. And then finally, you have to deal with skews in these lanes. So all of these are very critical. Next, we look at what Ethernet looks like today. A terabit Ethernet system typically consists of a Mac, then it will have a PCS, a Reed-Solomon forward encode error correction system, then finally SerDes. Then at the end is a transceiver which will connect the Ethernet Mac and the Ethernet subsystem to the fiber optic cable. Looking down here, you can see the details of the Ethernet Mac and the PCS and FEC. You can see the complexity in some of the blocks that you see there. So let's look at how do you test this terabit Ethernet. So my suggestion is to test layer by layer. Start at the SerDes, then go to the FEC layer, then PCS, then the Mac. So let's look at the SerDes implementation. Really, your target bit error rate for SerDes should be 10 to the minus 15. If you look at the SerDes, the architecture, you have the Mac, which is split into four 400G slices. Each slice has a PCS, and each PCS drives four FEC lanes and four SerDes lanes. So basically, SerDes has it's a mixed signal designs. It has the serializer encoder and the FIFO that are digital, and the modulator and the FFE, which are mixed signal. So how do you test the SerDes? You can do the eye diagram analysis, PRBS pattern testing, look at jitter tolerant signal integrity, as well as loopback modes. And for that, you need a PRBS running at terabit rates, and you need a 200G class bit error rate tester. So how do you test the PCS? So if you look at PCS, it looks not as many blocks, but these are all very difficult blocks to implement because they all do with multi-lane management and multi-lane alignment and skews. So PCS can have many skews. It's basically you can test the block mapping, the scrambling, descrambling, lane alignment, encoder, decoder, and lane distribution. All of these require some type of pattern generator with, so in some cases, error injection, some lane skew injection. But primarily what you need for PCS is a pattern generator. So let's come to the Mac now. For the Mac is a very complicated, very sophisticated system, especially for Terabit. You have frame generation, you have CRC integrity checks as well as flow control and LRR if you have Ultra Ethernet. And a 1.6T Mac will require a terabit traffic generator, which is what we call a terabit BIST. This is an on-chip generator which drives line rate traffic and can drive multiple modes. All right, and then it has to, because typically terabit Mac supports multiple ports, so you have to support multiple ports and into multiple per port pass and fail. And then if you look at the test matrix, you have to test framing, you have to test CRC integrity, you have to test address filtering, flow control, interpacket gap, frame size where you can vary the frames from 64 to 9 jumbo, and maybe even violate the frame size standards to generate error packets. And then finally, multi-slice testing, because typically, as you said, the Mac consists of multiple slices. So you want to be able to test slices in multiple configurations. All this requires a very sophisticated traffic generator, which can not only do line rate, terabit level generation, but also support VLAN tags, emulate congestion, inject errors, as well as give you support for multiple frame lengths and presumably random frame length generation, and then also support all the multiple slice modes. So, in a summary, what you need is for SerDes, you need PRBS generation in silicon. For FEC, you need error injection capability in silicon. For PCS, you need skew measurement in silicon. And for the Mac, you need a traffic generator. So, that brings us to how Imparé helps in these areas. We have IP cores that are designed for test and debug of terabit solutions. So we have a terabit BIST, what we call terabist, and then we have a terabit debug engine, which we call Terascope. So, if these are designed to help you ship terabit silicon. They provide support for observability as well as built-in self-testing. So if you look at a typical AI chiplet architecture, you have the Terabit, which connects to the Mac, and the Terabit Ethernet adapter, which will be sitting with each Mac. And UCI controller with the Terascope, UCI adapter, protocol adapter. And then there's a chiplet access manager, which controls all of these adapters and BISTs. You can have multiple BISTs in a system, multiple adapters in a system. So you can have as many Macs as you want in a chiplet, and it'll allow you to control those all through a diag, which is then goes to the system test controller. So overall, a very scalable, very powerful system. So what is a terabit? Terabit is a 1.6 terabit packet generator. It supports, like we said, multiple segment modes. One port, which is 1.6T, or two ports by 800 gig, 4 by 400, or 8 by 200. It can generate random packet lengths or and deterministic packet lengths depending upon how it's configured. And the packet length can be between 64 to 9K. It can also do CRC poisoning. It has an integrated PRBS, supports local and remote loopback modes. And like I said, the architecture is scalable. It supports up to 64 bits in a single chiplet. So one bit can do 1.6 terabit. One chiplet will do 102 terabits. So if we can put up to 64 bits in a chiplet, and then you can have up to 256 chiplets in an SoC. So you can do up to 26 petabits in an SoC. That's a very, very powerful capability. And you don't have to pay for all of it, you only pay for what you need. So the next is debug, because yes, you tested, you found. Now, when you run tests, you're going to find some failures. So with silicon, with terabit silicon, all these signals are very hard to get to in silicon, especially. You can't probe these very easily. Um, so you need something to give you in silicon visibility. That's a Terascope core. It supports Ethernet, LRR, UCIe, AXI, and HV. It has protocol adapters for each one. It has logic analyzer support for all of these, as well as protocol checkers. Um, so it can do hardware breakpoints, as well as trace mode, where it can trigger on specific events that you program. Very powerful breakpoint capability. It can do single step. It's got protocol aware transaction capture, um, sequential triggering, and it of course has a lot of counters which allow you to build histograms at the system controller levels, and you can get much more than just individual statistics. You can see how the system is performing. So a very simple use case, which is of a CRC error, EPS snoops the Ethernet system. It detects a CRC error from its tap. The flag is the error flag. This error is tagged to the sequence number, and then it builds a trace and sends that to the protocol adapter controller, which then sends it to diag. So now the diag has all the packet state it needs, everything that it needs to know about the packet is there. So user can then debug. Now, if you want to recreate it, they can use the BIST, and in the halt mode, the TeraBIST will generate packets with errors, with CRC errors, and then whenever the Mac detects the error, EP will detect the error at the same time, and it will compare expected errors with actual errors, and the user can then use that to debug and recreate errors and debug them in a controlled environment. One very simple example. There are lots of other use cases where Terabit can be useful. Please see your LinkedIn posts for those details. So, in summary, Terabits, very scalable, very high bandwidth packet generation, and PRBS generation. Essentially, terabit speeds from terabits to petabits. It tests Ethernet from MAC to PCS to the SerDes. It's configurable length packets. It can do corrupted frame generation, and it supports loopbacks. Very powerful again for testing Ethernet. Terascope gives you the visibility in today's very complex designs that you don't have today. It you can do triggering, very complex sequential triggering. You can do very complex breakpointing. Um, it gives you memory dumps. You can have very programmable run, halt, reset control. And you have watch points for breakpoints, and then it has pre and post triggered trace buffers that you can see, and then all the traces can be exported off chip, so you can look at the data and debug. So again, a very powerful debug engine that is much needed in today's very complex AI chiplets.
Thank you, Faisal, for sharing your wisdom and experience with us and also showing us how Impare's products are solving these problems. How can someone contact you and Impare team?
So the contact information is given here. I have my LinkedIn link there. As well as if you need more information, you can email Mustafa, or you can always go to our website at the web link we provided.
Thank you, Faisal, for joining us today.
Thank you, Rahil.
Thank you, everyone.